We are the IR Demister senior design team who consisted of Griffin Hanna, Thomas Norby, Matthew Zotzman, Jake Dijon, and Carson Dagenhart, who is the team lead. Our project was sponsored by Ingersoll Rand Incorporated. Ingersoll Rand is an S&P 500 company that contributes to various machine equipment technology. These include but are not limited to power tools, lifting products, and air compressors. Our team was tasked with creating an electrostatic oil demister for a rotary screw air compressor. Shown here is a picture of one model of air compressor that the demister would be implemented into, although there are several different sizes and models that it could be integrated in. The purpose of our subsystem design is to improve the efficiency from the current coalescing filter being used. The system's purpose is to remove all the oil mist coming from the high-speed moving components in the air compressor before the air is vented into the environment. As you can see here, this is the current design that Ingersoll Rand uses. It is essentially a metal box with an inlet and outlet. Inside, there is a steel wool ball that the air will pass through to remove the oil. The new design utilizes positive and negative forces to improve upon this design. On the left is a cutaway of our CAD model. The bottom section, or also known as the ionizer, consists of several layers of stainless steel mesh separated by PVC spacers. As the air flows vertically through, the oil particles will receive a negative charge before moving into the upper portion of the demister, also called the collector. The now negatively charged particles will be attracted to the sides of the hollow tube that is positively charged, and this will trap the oil before it reaches the environment. The team was also able to create a fluid flow model to show how the oil mist would be dispersed inside of the demister. This allowed the design to be fine-tuned where the collection surface was oriented in such a way that maximized the efficiency of the device. The different pieces of the laser-cut steel outer housing were then welded together, and many holes were drilled on the side tabs, which were used to secure the lid onto the rest of the design. Looking down into the tube, you see the lower ionizer as well as the inlets for both our negative and positive charging wires. Attached to the lid is the collector. One may notice how it is separated from the actual cap by a PVC disc. This helped with the safety of our device and acted as an insulator to absorb any electricity. The disc was secured to the cap by 4 nylon bolts. A rubber ring was also added around the edge to ensure an airtight seal inside when the upper and lower portions are put together. The last part of the build that was implemented was an air blast system that is designed to push gusts of air at various time intervals. This will clean the side of the collector off to maintain maximum efficiency when attracting the oil particles. With the design and fabrication finished, the team was invited to the Ingersoll Rand factory in Davidson, North Carolina, where we had the privilege to work side by side with one of their technicians to install and test our design inside the machine itself. After installation, the machine was run a number of times, showing that our design met the specifications given to the team and proving that our project was a success.